Today I'm going to be explaining the Standard Model of particle physics. So what is the Standard Model of particle physics? It's basically a model that describes every type of elementary particle that we know to date and the laws that regulate these particles. So, well, what particles do you have? You have two categories of particles: fermions, in great handwriting I might add, and bosons. So, these two categories are very different from each other. Now, you can look at my video Fermions versus bosons for more direct information on this, but to be short about it, fermions are traditional particles of matter. So, you can't have multiple fermions in the same quantum state. There can't be multiple fermions in the same place at the same time. Bosons, on the other hand, there can. They can occupy, multiple bosons can occupy the same quantum state. This is because bosons are force-carrying particles. Now, some bosons you might be familiar with are the Higgs boson. This boson, if it exists, would carry mass. Now, the other bosons, you're familiar with, such as the photon, right? The photon is a particle of light. It carries the electromagnetic force. So anytime you use a magnet, well, you're using photons. So, these two basic categories. Bosons have an integer spin, right? These particles are basically spinning around with an integer number. Fermions have a half-integer spin, which is just integer over 2. And very simple. So, for some bosons, right? We also have antiparticles, right? So, for all these fermions, right, we have like electrons, and we have like electron neutrinos, which is like that. We have muons, which is that, and muon neutrinos. And you have tau and tau neutrinos, right? Those are some fermions. You also have the quarks. Up, down, strange, charm, top, bottom. Right? So these are all your fermions. For bosons, you have, in the Standard Model, the Higgs boson, the photon, which is like that. I'm pretty sure. You have the Z boson, which is like Z neutral, and you have the W boson. And, you also have the gluon, which is just G, I think. Anyways, so you have all of these bosons and fermions, right? But you also have their antimatter counterparts. So for electron, you would have the positron. For, obviously they have to have charge to have an antimatter counterpart, so something like the Higgs and the Z boson, no antimatter because there are neutral particles. They don't have a charge. Particles like the up, down, strange, charm, top, bottom, electron, muon, and tau, W boson, all have antiparticles because the W has a plus or minus charge. Okay? So these are all the particles that are part of the Standard Model. The Standard Model describes how they all interact together. Okay? So, how do these particles all interact together? Well, you have particles like quarks, right? Quarks love to stick together, and they love to stick together very fast, and this forms particles known as mesons or byrons. Byrons composed of 3 quarks, so byrons and mesons. And this is not including antimatter particles, but I'll just put a plus and minus and a plus and minus, and I guess we only have a plus and minus on the W. I'm pretty sure gluons have no charge. So these are all the plus and minuses we need. So we're including antimatter particles when we talk about everything here. I'm just not going to mention that from now on. And so, for the byrons, we have 3 quarks, consist of 3 quarks, and the mesons consist of 2. The mesons consist of a quark and an antiquark. So you could have an up and an anti-down, right? I'm just going to make minus antimatter and just nothing matter, although electrons are matter and they have a negative charge, so, but just from now on. Okay, so you could have an up and a down, okay? You could also have something which is an up and an anti-up. This is what's known as, well, actually, we'll go bottom and anti-bottom. This is what's known as bottomonium. It's the particle paired to its antiparticle. Because mesons are a pairing of a particle and an antiparticle, specifically for quarks, they last for a very short amount of time. Not much time. Mesons don't exist for very much time at all. So, very short-lived. Byrons here, these are three quarks. These include the familiar proton and neutron, which are up, up, down, and up, down, down. Right, those particles very stable. In fact, neutrons are stable for 15 minutes. Protons, which are up, up, down, may be completely stable. They may never decay, or they may decay for 10 to the 35th years, which is, longer than any of us will exist. So, in 10 to the 35th years, all our protons may be falling apart, but for now, I think we're safe. But these byrons and mesons don't just consist of the quarks, right? Byrons you could have up, up, down, or strange, charm, bottom, right? You also have anti-byrons made of antiquarks. The one thing to remember with byrons and mesons are top quarks don't form them, because these couple the quarks together using the strong force, which we're going to talk about next. The top quark happens to decay faster than the strong force can pull it together, meaning you will never find any quark except for the top quark just alone sitting there, because it always forms up into particles like byrons or mesons so fast we can't see it. The top quark, on the other hand, decays so fast that it doesn't have a time to form quarks, or to form byrons or mesons. Thus, you can't see a top quark directly, obviously, it decays way too fast, but you can see the products of a single top quark, and Fermi Lab has actually discovered one top quark that has never formed into a particle. This is pretty interesting because the top quark decays faster than it can form into a particle. So, what are quarks held together by? Quarks are held together by these gluons, right? Gluons carry the strong force, right? So, well, what is the strong force? Well, you could say the strong force is a form of the color charge, which I don't fully understand. But the strong force basically couples quarks together. So, the strong force acts very quickly. It acts so quickly that none of the other quarks, even something like the bottom quark, which is very unstable and decays pretty quickly, those quarks still have time to form up into particles like byrons and mesons, and can hold antiparticles and regular matter particles together long enough, for some amount of time before having them, annihilate instantly. So it's the strongest of all the forces, which its name obviously implies being the strong force. But basically, it's very strong. It couples them together. It also couples the so in the byrons, it also would couple like the protons and neutrons together in the nucleus of an atom. But that wouldn't be done with the gluon. That would be done with a meson or a byron. I'm pretty sure it's a meson, which would be a composite particle. But that I'm not going to talk about. I'm just going to talk about the regular particles in the Standard Model. Then you have the other fermions, the electrons and the muons and stuff. Those can be part of the it's called the weak force, which is as well part of the quarks. So what is the weak force? Well, the weak force is what makes uranium decay and stuff like that, right? So the weak force is W and Z bosons. Now, the Standard Model states that charge must always be conserved. So if you have negative charge coming in, you must also have negative charge going out, right? Pretty much is what it means. You must conserve the charge. Charge can never just vanish. You can never have negative charge and then have zero charge, right? That's you can't do it. So why do we have different bosons for the weak force when for all the other forces we only have one? Well, there is a simple answer to this, and this is that the Z boson has no charge. So when there is no charge change, such as in here, you would use a Z boson because it has no charge, meaning no charge needs to be conserved. The W boson has a charge, so this is why there can be an anti-W boson and a boson. When charge needs to be conserved, use the W boson. Well, actually, when charge needs to be conserved, you use both of them. But when there is a charge change and you need to conserve the charge, where a neutral boson wouldn't work, you use a W boson or an anti-W boson, which conserves the charge because a W boson or an anti-boson has a positive or negative charge. This can conserve the charge. Okay? You also have what's called the photon. Photon carries light. It's an electromagnetic force, right? So, well, what does the electromagnetic force do? It can couple your electrons. It does the fermions, right? And so, well, what's the electric force? What electromagnetic force? Well, what does it do? Well, it does magnetism. Also, if you have, say, an electron, right? These are what's called Fineman diagrams. If you have an anti-electron and an electron, They annihilate together, and they can produce a photon. This is the photon being a mediator of the electromagnetic charge, right? Well, not really, but this is a photon transferring the electromagnetic charge. But a photon deals with the electromagnetic charge. So when you use a magnet, those are photons, virtual photons. I should mention first, after what I say now, I'm going to mention something about bosons in the Standerd model. Anyway, the fermions, you have electrons, muons, and tau. Those are sort of electron we are all familiar with as in electricity. The muon and the tau are like heavier versions of the electron. Now, the neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino, all very interesting. They have low cross-section with matter. This means that they don't interact with matter much at all. Right? So, very tricky to see. They can also, we think, they might be able to change between the two. And we've also seen them traveling faster than the speed of light, although that isn't confirmed yet. So, very strange particles those neutrinos are. We don't really know much about neutrinos. So, all the bosons in the Standerd model. Bosons form a virtual field all around us. There are bosons all around. Now, these bosons are allowed to violate the conservation of matter and energy for a small amount of time because of the uncertainty principle. I won't get into the math behind it, because I don't really understand it. Anyways, these bosons are virtual bosons. We can't detect them, but we can certainly detect their effects. Because without virtual bosons, assuming the Higgs boson is real, nothing would have any mass. You couldn't play with magnets because there would be no virtual photons. Nothing would decay because there would be no virtual Z and W bosons, and nothing would stick together, and we'd just all be a soup of quarks. So, I hope this explains the Standerd model in all its glory. This is a model that holds particle physics together, and it stood for a long time, and I predict it will stand for a long more.